Welcome back! In the last lesson we discussed the architecture of a deep neural network, and how we can use linear models as a building block in our neural network to obtain nonlinear models which best classify our data. We also saw how the combination of lines with different weights and biases can result in different nonlinear models, some better than others depending on which input we assign more weight to. Now, how does the neural network know what weights and bias values to have in each layer? That way, the combination of our hidden layers can result in the most accurate model. Well, it's really no different than how we did it for the signal-based perceptron model. We're still making use of a gradient descent optimization algorithm which acts to minimize the error of our model by iteratively moving in the direction with the steepest descent, the direction which updates the parameters of our models while ensuring the minimal error. It updates the weights of every model in every single layer in order to obtain this final model. We'll talk more about optimization algorithms and backpropagation of deep neural networks in the next lesson, but for now it's important to recognize that subsequent to the training of our neural network by dividing our data samples through some decision boundary, the process of then receiving an input to produce some kind of output to make some kind of prediction is known as feedforward. Feedforward neural networks are the core of many important neural networks, such as convolutional neural networks, which we're going to cover very extensively in this course. But we've already seen examples of feedforward neural networks. It simply means there aren't any feedback loops or connections in the network, simply an input layer, a hidden layer, and an output layer. Although do note that there can be multiple hidden layers, which simply depends on what kind of data you're dealing with. The number of hidden layers is known as the depth of the neural network. Deeper neural networks can learn more complex functions. The input layer first provides the neural network with data, and the output layer then makes predictions on that data based on a series of functions, activation functions. The most widely used activation function is actually the ReLU function, which we will cover later on. To gain a solid grasp on the feedforward process, let's approach this mathematically. First, the inputs are fed to the network. We'll represent that as a matrix x1, x2, and 1, where 1 is the bias value. We saw that each input is multiplied by weights with respect to the first and second model to obtain their probability of being in the positive region in each model. This might seem a bit intimidating once we represent this mathematically, but I promise it'll make much more sense once we go through an example. So, to represent this mathematically, what we'll do is we'll multiply our inputs x1, x2, and b by a matrix of weights. We'll be performing matrix multiplication, which I'll demonstrate momentarily. But notice how the matrix is denoted as superscript 1, so as to denote the first layer. Ultimately, what that will do is give us the score of the point that's represented by these inputs in each model, and then as you know, by taking the sigmoid of our scores, it gives us the probability of the point being in the positive region in both models. Subsequently, the probabilities we obtained, we now have to multiply by the second set of weights. Notice how we always include a bias of 1 whenever taking a combination of inputs. This set of weights, if you recall, is responsible for the combination of the linear models in the hidden layer to form the nonlinear model in the output layer. As such, the inputs x1 and x2 which exist in our models are also multiplied by these weights and then eventually added up to obtain the score in this model. And as you know, to obtain the probability of the point being in the positive region of this model, we take the sigmoid, and thus producing our final output in a feedforward process. All of these equations might seem a little intimidating, but it's really easy if we look at an example. Recall the neural network that we had previously, with the following linear models in the hidden layer, which combine to form the nonlinear model in the output layer. Obviously, the nonlinear model is what best classifies our data. So what we want to do is use our nonlinear model to produce an output that describes the probability of the point being in the positive region. To do so, we'll use this representation of the multi-layered perceptron to carry out the operation. The point was represented by the coordinates 2 and 2, so that, along with a bias of 1, will represent the inputs. The first linear model in the hidden layer, recall, was defined by the equation -4x1 minus x2 plus 12, which means in the first layer, to obtain the linear combination, the score of the point in our first model, the weights that the two inputs are multiplied by are -4 and -1, and the bias value is multiplied by 12. To obtain the linear combination of that same point in our second model, the weights that the two inputs are multiplied by are -1/5, -1, and the bias value is multiplied by 3. By performing matrix multiplication, which I've already shown you how to do in the NumPy crash course, you end up with the linear combination value. The score of the two inputs in each model in a 1×2 matrix. The score of the point in the first model is 2, the score of the point in the second model is 0.6, and now, according to the equation we previously derived, to obtain the probability of the point being in the positive region relative to both models, we simply apply the sigmoid to both points, which recall is 1 divided by 1 plus e to the negative x. This gives us a probability of 88% of it being positive in the first model and 64% of it being positive in the second model. Now we're at the second layer, and the second layer, recall, contains the weights which dictate the combination of the linear models in the first layer to obtain the nonlinear model in the second layer. In our case, our algorithm determined weights of 1.5, 1, and a bias value of 0.5. So now, continuing with our equation, we have to multiply our probabilities from the first layer with the second set of weights, and don't forget to include the bias value which we have in each layer. Multiplying this to the set of weights 1.5, 1, and 0.5, this results in a final score of 2.46. Taking the sigmoid of this gives a probability of 0.92, and that right there is the math behind the feedforward process, where the inputs from the input layer traverse the entire depth of the neural network, and based on a series of sigmoid functions and linear combinations that it goes through from one layer to the next, eventually it reaches the output layer, which makes a final prediction and produces the final output. In this example, it only had to go through one hidden layer, eventually producing an output of 0.92. Whether you have one hidden layer or 20 hidden layers, the computational process is the same. Now let's imagine that we had a really bad model, which places most of our red points in the positive region, even though we know they should be in the negative, since they've been labeled as such. Obviously, this model has a very high error. We need to train our algorithm to come up with a better one. And that's exactly what we'll talk about in the next video.